So we're delighted to have Isobel Kolbé back to UCT virtually to give us a talk today. Isobel is a lecturer in the School of Physics at Wits. She received her PhD in 2019 from UCT before doing research visits at CERN and BNL, followed by postdocs in Seattle and Santiago de Compostela. Her research interests involve the theoretical understanding of matter at the highest temperatures and densities producible on Earth, and indeed since a microsecond after the Big Bang, with particular focus on the physics of jets and the quark-gluon plasma. We're going to learn, coming up on jets, about Monte Carlo event generation for jet physics and heavy ion collisions, for which Isobel is one of the world experts. So delighted to have you. Thank you so much for taking the time.
Awesome. Thank you very much for the invitation and for that sort of very kind introduction. It's real pleasure to be back at or to be quote unquote back at UCT. I would have liked to have been there in person, and I will endeavor to come over and visit in January or February. But it's such a pleasure to be back and to talk about this physics that this is now a little bit different from what I worked on in my PhD, but it is still related. I will talk next week on a little bit more related to the things that I worked on when I was back at UCT. But this, I think, is something where I've tried to approach the problem in a different way. And so I had to learn these Monte Carlo types of things since my PhD. So I was never trained formally in these things. Another thing that I wanted to say was that it's a little bit daunting to follow Björn Schenker. He is world-renowned for being one of the best speakers in the field. And so, but I will try my best. What is nice about it, though, is that it does mean that you had a very good introduction last week on some of the physics that I make use of, but don't actually work on myself. So the first thing I'm going to try to do is sort of recap the heavy ion physics a little bit, just to touch on what Björn was speaking about. And then we'll go on to jets and Monte Carlo. And then next week, we'll talk about small systems and how we use these techniques to really sort of tackle the small system problem. I will also say, please feel free to interrupt me at any time to ask questions or just sort of object. Very good. Okay, so let's start with a quick recap on the heavy ion physics that Björn really sort of covered very well. The first thing I'm going to show you is maybe not something that is from Björn. This is, in principle, it's a heavy ion simulation, but this is really from URQMD. It's quite an old simulation. URQMD is ultra-relativistic quantum molecular dynamics. So in this simulation, you won't see the fluid that Björn was talking about, but it does sort of capture a little bit of the physics that we are talking about. So there will be these highly Lorentz contracted nuclei that are coming in, that have now been accelerated around the beam, and they are coming into this collision region. They collide and they deposit a lot of energy in the central region, and they produce a lot of particles that carry color charge. And then this sort of system expands very rapidly, and as it expands and cools, it will you'll see that it's sort of these colored objects hadronize into uncolored objects or color neutral objects. Now, of course, even though we tried this earlier, I didn't think to check this. So let's see if we can get this to work. So maybe it's the laser pointer that's causing problems. Yes. Okay, very good. Okay, so in come the nuclei from the side, and they collide, and there are all these particles that are flying off. You see that there's no fluid, there's no hydrodynamics here, but in this simulation, at least, everything sort of flies off and you create a lot of particles. The reason this is useful to have in the back of your mind, even though it does not capture all of the physics, somehow it's useful because, okay, it creates this image of these colliding of the system, the different stages of this collision. And then, of course, you really do see all of these particles that arrive in the detector, and you can immediately see how this is a problem already. Experimentally, this is a problem. There are just far too many particles, and this will cause us a lot of trouble. Okay, so now let's see if we can move on from the slide. Okay, very good. Okay, so what at the end of the day is the major problem that we have to deal with is these lots of particles. So if you have just a proton-proton collision where there aren't so many particles, this is a real event display from ATLAS, from run 2, a dijet event. And what you see is that even with pileup, so in the proton-proton event, even with pileup, so you you have really bunches of protons that are crossing each other, and they're colliding all in this sort of same region. And so you might have several proton-proton collisions per bunch crossing. But experimentalists are very good at this, and they can sort of simplify the what's happening here, and they can decide, they can figure out which particles are coming from which collisions. And so you can really sort of see, okay, we'll draw these colored lines for the particles of interest from this collision, and we ignore the rest. And so you see a very nice and clean system, even with the pileup. So here's the calorimeter display, and so you see there's lots of particles that are produced back to back. And it's very sort of clean in the sense that what you're able to get rid of a lot of these background problems. Now, I'm trying to pretend that this is easy. It's not. This is what a lot of proton-proton experimentalists spend a lot of their time doing, is trying to clean this up. But at the end of the day, it looks kind of, it looks very nice. I can measure the energy of this jet, and I can measure the energy of that jet. And so, but in a heavy ion collision, this you already saw from Björn last week, the situation is very different. This is also an Atlas event display, but now for lead-lead. And again, it's a dijet event. And you might not immediately see the dijets, which is part of the point, but you see that even with just the one collision, there's no pileup here. You don't have several collisions here. What you have is just the one, but each of these colored lines is a particle that has come off of your material, off of your medium. And you still can see some of the structure. You do sort of, here's a very high energy jet coming out here. That's very nice. But already I can see that behind this jet, where I was expecting this back-to-back, sort of quark, anti-quark production, I see that behind it, it's nowhere near as clear. I can't really see what's going on here. And on top of that, there is a lot of activity in other places as well. I can also already see that, maybe there's some structure over here and there's some structure over here. Okay, so it's a lot more complicated. And what creates a lot of this complexity is the fact that a lot of the physics that's happening here is happening on a finite time scale, in the sense that things are happening in order. Whereas in a proton-proton collision, you can really you really have a lot of your physics happening all at the same time, and you don't have to worry so much about what happens first, what is produced first, and how is this thing interacting with that thing. But here it's clear that there was some sort of production that happened, and then there was some interaction. And we also know that there's like a lot of evolution that happens that results in these other structures. And so we have an additional dimension here, which comes from not just the large numbers of particles, but also this sort of time structure of what's happening. Okay, so I wanted to, let's talk about a little bit about how you go about modeling this time structure. So this is an image that you will have seen several times in this environment, of course, but sometimes it's nice to see things you have seen before. And what we're going to talk about is all of these different stages of modeling the heavy ion collision. And some of it, of course, is done analytically. There's a lot of work that's done analytically to model the different stages. But the focus of this talk will be all of the different Monte Carlo methods for modeling these things. And what we'll see is that it is in fact possible to combine all of these different stages. Okay, so what we'll start off with talking about what the initial condition, the really sort of, okay, I'm going to say the word initial condition. I'm not talking about the initial condition for the hydrodynamics. I really mean, what are the things that you are colliding? So you are in a proton-proton collision, it's clear you are colliding two protons. In a nucleus-nucleus collision, fair, you are fine. You can be blasé and say, okay, I'm colliding two nuclei. But these nuclei have a structure that is very different to just a superposition of protons and neutrons. It's not, if you are colliding two lead nuclei, 208 nucleons with 208 nucleons, that's nowhere near the same thing as doing 208 individual nucleon-nucleon collisions. Because of course you understand that this must be true, that a nucleus is not the same as just 208 nucleons, because you have a lot of positive charge that's sitting inside this nucleus. Something has to be holding it together. Okay, we know that this is the strong force. The strong force is holding this nucleus together. But that means that all of these nucleons are correlated with each other, that they are interacting with each other. There are very strong interactions there that are changing the way that the structures of these individual nucleons can be extracted from just proton-proton collisions. So this will be our first major problem, is what exactly is it that you're colliding? How do you find out what this distribution is? Okay, good. Once you've decided what you want to collide, you now have to do something which we, up until very recently, have just simply not done. We've just ignored it. So you collide your nucleons, you deposit all of this energy in the central space, but then what you are left with, what you have in these first, like, very, very early stages, so we're talking here about sort of less than 3 Fermi or so, 0.3 Fermi, you have a very far from equilibrium medium. This is something that, so this language is also abused a little bit, because we talk about hydrodynamics, the work that Björn was talking about. We talk about that as being in equilibrium. Of course, there's no temperature equilibrium there. There's no pressure equilibrium there. But at least we have some notion in the backs of our minds that you have had time for a lot of collisions to happen, for there to be some sort of equilibration. But in this pre-equilibrium phase, it's not clear what's happening there at all. And a lot of people have worked on this. You've sort of tried to think about how you do maybe some like QCD kinetic theory or something there. But the major problem that we have as jet physicists is that we don't know what the evolution, what the effect of this pre-equilibrium phase is on the evolution of the jet. And so what we've done, and that's partly because our models depend on a temperature, you need a temperature, but it's impossible to talk about a temperature outside of equilibrium. There is no such thing as temperature before you've equilibrated. And so that will be the second problem, is what do you do in this pre-equilibrium phase? Now that problem, for the purposes of today's talk, we will just ignore. We will do the same thing that everybody has done, and it's just to say there is no temperature, so that we don't know what the temperature is. So the temperature is just 0, or it's just some linear thing or something easy. We'll ignore it for now. But next week, when we talk about small systems, of course, you're dominated by these early phases. So then next week, we'll come back to this like early stage over here. Okay, good. Now I've spoken almost for 5 minutes, and we've only gotten sort of a third of the way into this diagram. But good. So now you've collided your nucleons. You've decided what you want them to be. You have made some statement about how you think you get from this this very far from equilibrium phase into some equilibrium phase. And now what you start off with is this initial energy density. So now you have some deposited initial density that you are going to give to your hydrodynamics and evolve. Okay, so you start off with some energy density, which gives you temperature profile, and it gives you, which in turn gives you a pressure profile. And so you can evolve this using all of this physics that Björn spoke about. So you have this like viscous hydrodynamics, and all of this is sitting in the background. And that's at this stage, as far as the field goes, this is now very, very sophisticated. We have really sophisticated models for the hydrodynamics. Okay, then you have to, once you've evolved everything, at some point the temperature comes below the critical temperature, which means that you can no longer have asymptotically free quarks and gluons. So there has to be some hadronization process. Again, from a Monte Carlo perspective, this is a problem. It's difficult. We don't know exactly what the hadronization mechanism is. And it turns out that not only does it depend on which system, not only does it sort of really depend on who you ask. So if you ask a heavy ion physicist, they have some idea in their minds for what they think the process is. If you ask a proton-proton physicist, they think they know what that process is. But at least those two processes reproduce the same data. What you find is that the hadronization in E plus E minus collisions, just from looking at hadron multiplicities, you find that, in fact, in nature, it appears as though the hadronization process depends on the system that you're looking at. So this is a gnarly problem. And in good fashion, we will also partly just ignore it. We will just take some very simple model and use it there. Again, then I'm not even really going to touch on these later phases. These are sort of pretty standard, and they're used in proton-proton and also in lead-lead. And so that's not really, we won't talk a lot about that. But in the end, what you have to have is that you have to have some way of evolving these hadrons where they are still interacting a little bit with each other, and then at some point they free stream to your detector. Okay, the last thing that I will say about this diagram, which is not on the diagram, is that, of course, this talk is about jets. So what we want to do is we want to ask, okay, at each of these phases, what is happening to the jet? So how do you produce a jet? First, you have to know what the nuclear, what it is that you're colliding. So, and then you pull a jet out of that. What does it mean for a jet to evolve over this this pre-equilibrium phase? Can we model the interaction of the jet with the hydrodynamic phase? And then what is happening to the jet in the hadron phase? Okay, so that is a quick, just a brief overview of what something that you maybe would have already heard, but I wanted to just pause and see whether there were any questions. I can't see any chat, so someone would have to shout.
I have a question. It's so this diagram is specifically related to collisions, but it seems like there's a lot of similarity in the cosmological perspective, where you have early phases of the universe. Is this pre-equilibrium dynamics period considered to be something similar to the reheating era, and where you have this initial energy density point where you get the quark-gluon plasma phase? That's where things start having temperature and where you can describe things. And I was wondering how people are researching the pre-equilibrium dynamics. As you were saying, people are doing some QCD dynamics research over there. Like, is that something that you can say anything about?
Yeah, that's a really, really interesting question. I do not know the answer. What I will say is that this analogy with the very early universe is, I say it's not really an analogy. It's fair. This is the physics of the very early universe in some regards, because okay, it's true. You have asymptotically free quarks and gluons, and you have these very, very high temperatures. You have these very high densities. That's all fair. But there's a major difference, a really, really big difference between the collisions and the early universe, and it's this notion of the expansion of this. Of the finite size of this droplet that you are creating. So even though the universe is expanding very rapidly, it's not expanding at all in the same way that we think of the expansion in these collisions. In these collisions, we have really just a very sort of a small droplet that is surrounded by a vacuum. That's not the same as what's happening in the early universe. So you have this sort of surrounded by vacuum, and we try to draw these analogies, try to look for these sort of similarities, but that's a very difficult thing to do, even when we're not talking about this pre-equilibrium phase. Now you ask the question about the pre-equilibrium phase, and this is poorly understood even in these heavy ion collision environments. It's poorly understood, and we can do this experiment over and over and over again, right? In the universe, you only have the one, and so you have very poor statistics for the universe. But we can do these experiments over and over again, and we can control things and shuffle them around a little bit. And even then, we don't really understand this pre-equilibrium phase very, very well. So I do not really know the answer to your question. And I'm not sure that if anyone has sort of asked, is this how does this relate to this sort of this reheating phase and so on? Yeah, but it is quite difficult even at this stage. Okay, good. So let's I just want to touch very briefly on some of the ways that we do all of these different phases, and then we'll get to jets. So we're still on the heavy ion recap, but so the first thing that is sort of important jargon for this conversation is we were talking about the initial condition. So I'm going to collide these two nuclei, and the first thing is that I need a notion of centrality. So this is this plot on the left-hand side. If I do some large number of collisions, they're of course not all going to be head-on. So if they're very head-on, very, very central, then this overlap is large. It's a very small percentage of the collisions. And so 0 to 5% centrality means that you are looking at very central collisions. Okay, and then you sort of go more and more peripheral. And it turns out that, of course, the vast majority of your collisions are quite peripheral. Okay, good. once you've established this, you now need some way to model where you're going to deposit the energy. And this is usually done in something called Monte Carlo Glauber. So you overlap two Woods-Saxon functions. So that's on the right-hand side here. I overlap two Woods-Saxon functions, and I have in this specific model here, I have a size for each nucleon. And then I sort of ask, okay, I've decided the centrality, and then I ask how many of these nucleons are colliding. And once I've got this, and I do this in a sort of a controlled way, but it's still a Monte Carlo way. So I've distributed these nucleons across the nucleus, and now I can deposit energy in this region. Okay. What, of course, now the question is, now I've only got now from my Monte Carlo Glauber which nucleons will overlap. I now have to ask, okay, once I've overlapped them, how much energy am I pulling out? So I really need to do now some 2-to-2 scattering of the partons in these nucleons. And I have to ask, how much energy am I pulling out? And for this, I need something called the parton distribution function. So what I have on the left-hand side here is the parton distribution function for the proton. So the proton, so okay, the way to read this plot is that on the x-axis you have Bjorken x. This is the fraction of momentum carried by the fraction of the proton's momentum that is carried by a given parton. And on the y-axis you have, okay, this is the parton distribution function, but multiplied by this x. So it's not really, this can go higher than 1, so that's not really what you're looking at. But at least what you can see is that, okay, fine. If I'm looking at sort of a tenth or so of the momentum of the proton, I have twice as many up quarks as down quarks. Okay, so that's plus minus how I read this plot. Of course, you see that it's not a third, right? I'm not sitting, these peaks aren't over here at a third. They're sort of significantly less than that. And that's because a huge amount of the momentum of the proton is carried by other things. So on this, here's the gluon curve and the C-quark curve. So now the gluon curve and both of these curves have been reduced, right? Divided by 20. So that they really sort of actually are shooting up out of this plot. And okay, I always wondered, when I was a student, I wondered how you get this plot. Okay, you have to, you need several ingredients, but I found that the sort of, a nice way to think about it that's maybe, it's maybe a little bit oversimplified, but a nice way to think about it is to think about the, if you think back to in undergrad when you were solving a differential equation, you have these 3 ingredients, right? So you have a differential equation, fine, and then which has a solution and an initial condition. So you have these 3 ingredients. And what you would usually be asked for in a test is you would be given the differential equation and the initial condition, and then you would be asked to find the solution, right? Now, what you do here is something that's very similar, except that you experimentally, you measure the solution. So you measure the solution experimentally at some scale. So you can measure this at different scales. And then you guess the differential equation, DGLAP or whatever it is that you want. So you guess the differential equation, you measure the solution, and then you can extract the initial condition. And so this is the initial condition that is evolved through your differential equation, which evolves your distribution function in different momentum and x scales. Okay, so just to sort of, I don't know, I always thought that this plot was a little bit mysterious, but you have to, you see that there is an experimental, there are uncertainties here that are experimental, they're from the model, there are also some from parameterization, and that's because of this guesswork that you have to do. You really are doing some parameterization, and of course, you then fit to a lot of, it's a global fit to a lot of different experimental measurements. And so it's a little bit more complicated than what I was explaining, but it's essentially that. Okay, good. So, but of course now I've made a big spiel about, we're sort of thinking about this, this stage of the collision. I've made a big spiel about the lead nucleus not being a superposition of protons and neutrons. It's really a little bit more than that. And you can ask, can I measure that? And so lots of people have worked very hard on this. And what you find is something like this. So you really need not just a parton distribution function, you need a nuclear parton distribution function. So this plot in the middle is the ratio of the nuclear parton distribution function divided by the proton parton distribution function. So I'm really asking how different is the distribution function, the PDF in the nucleus to that of a proton. And the first thing you notice immediately is that this is never one. This is, well, okay, it's one for these, like, here are some places where it's one, but it never sort of settles down to one. On the one hand, you have here at the very low X region, you have gluon, you have shadowing. This you can understand in terms of the CGC. You have this like saturation from the gluons, and these like gluon recombination means that you get a suppression of this parton distribution function. You also see a bunch of different other features. You got like there's this anti-shadowing, there's an EMC minimum here. And the important point to make here is that this curve, okay, and these other ones are for different parameterizations, but this curve comes out of the data. There's a parameterized function that you extract from data, and so you've not put any physics in there because we have the notion of a color glass condensate. We can sort of think we understand the physics of what's happening here. What's happening here is not so clear. And there are different arguments and different interpretations for this, but at the end of the day, this is what the data says. So this is what is happening here. Okay, so what you extract is this plot on the right-hand side. This is the nuclear parton distribution function for the up quark, and for 3 different of these PDFs, these NPDFs. There's ePPS, there's NCTEC, there's NNN-PDF. These are next to leading order calculations, and so on and so forth, each with their errors. Okay, so it's just sort of to show that this looks very, okay, it's not so very different here, but the shape definitely at low X is very poorly controlled. This will improve with the electron-ion collider. So when you have, because when the electron-ion collider will produce more data at sort of smaller and smaller X, so that you can constrain these a little bit better. Okay, so I've overlapped my nucleons. Do you have a question? Can I hear something? No. Okay, so I've overlapped my nucleons. I've now decided in my 2-to-2 scattering what my incoming momenta are going to be using these NPDFs. This will be important also for the jets later on, but it's also important for the modeling of your background medium, your QGP. Okay, then there's the hydrodynamics. I really want to not say too much about this, but just in case you missed Björn's talks the last 2 weeks, what we know has to happen then is, okay, we're skipping this pre-equilibrium phase, but after some time, you have enough collisions in this very high density medium that you are able to do something like have pressure gradients transform a spatial anisotropy into a momentum anisotropy. So here I'm drawing, I'm looking down the beam, I've got these 2 nuclei that are colliding a little bit off center, and they deposit a lot of energy and energy density in the middle, but outside is essentially a vacuum. So you have this very high density in the middle and then a vacuum on the outside, which means that you have very steep pressure gradients. But because this distance is shorter than that distance, than the vertical distance, you have steeper pressure gradients in the horizontal direction than in the vertical direction. And so that means that steeper pressure gradient means higher force, and so you get higher momentum out in this horizontal direction. And this was measured like almost immediately when they turned on RIC. You can see this, here's the number of particles at some angle, and you see that there's this very clear modulation, and I can do a Fourier transform of this, and I can fit these Fourier coefficients and extract something called the V2. Okay, and the critical point here is that I can only do this if I have a hydrodynamical description of this plasma. I really have to have some sort of fluid description of the plasma. Okay, I put here 2 codes I wanted to. So music is the one you learned a lot about from Björn last week. Trajectum is another code that is also publicly available and is very quick to run, very easy to run, and also contains all of this physics up to here. All of the physics, the sort of initial condition, and they have a sophisticated pre-equilibrium phase actually even, and it runs like super fast, and you can just download it off their website. I've put the links up here, and I will share the slides in a bit. I wanted to point out trajectum because next week I will talk about some results for jets on a trajectum background as opposed to a music background. So I just wanted to sort of say these words so that you've heard them before. Okay, good. So now let's talk about jets very quickly. So good. What we want to be studying, which is now different from this plasma by itself, is you ask the question, how can I measure things about the plasma that are sort of independent of the plasma itself. And the problem is that when you do this collision, this plasma only lives for a very, very short amount of time. So you can't keep it somewhere and shoot a laser at it. If you just do the back of the envelope calculation, you find that, okay, your nearest detector is a centimeter away from the collision point. You produce something that lasts for a few yoctoseconds, 10 to the minus 23 seconds. You shoot, even if you knew exactly when the collision happened and you turned on your laser a centimeter away, at the speed of light, which is only 10 to the 8 meters per second, by the time your photon reaches where the collision happened, the plasma hasn't existed for more than 1 million times its own lifetime. It's like trying to look at the dinosaurs by taking a picture now. It's really so it's impossible. But what you can do is look at things that are produced at the same time. So when we were looking at these PDFs, we asked the question, when I do my 2-to-2 scattering, what is the momentum of the outcoming particles? And occasionally, and sort of, you can work this out, there's a spectrum for this momentum, and occasionally you will produce particles that have a very, very high momentum. And because they have this very high momentum, they don't equilibrate with the medium as quickly. So they are essentially in some sort of unequilibrated state for much longer. So they are in some sense independent of the medium. And what will happen, of course, is that you produce them in quark-anti-quark pairs. So I've taken this background picture is from Björn, in fact, it's their simulation, so that's music. And then I've drawn here sort of a back-to-back quark and anti-quark pair. And what happens is that one of the quarks moves through the medium in a shorter distance, perhaps, if you're lucky, and the other one will move a longer distance. And the argument is that one will lose more energy than the other. And this turns out you can see immediately in data. So what I've got here is the calorimeter from CMS. So you should imagine this as like, if you take an A4 piece of paper and you sort of wrap it around along its long side, then that's your barrel. That's the sort of barrel detector. And you've got your beams coming into either side. And what you see here, this very high tau, this is a high momentum jet. And the back-to-back one, the one like right back to it, has lost a lot of its momentum. So even though I know that they started off with the same momentum, so I can argue, I can say, oh, I actually think maybe this one traveled a longer distance than this big one. There are other effects here, of course, as well. If you look carefully, you'll see that it's not just that this tall tower is much taller than the other one. It's also much narrower. So they've done a good job of drawing the colors here for us, but you can see that these, as long as you're not colorblind, you can probably see that there's this sort of red region which is much broader. And so it's not just that the energy isn't lost to the medium, it's really distributed out of the cone. Okay, and the main observable that we have for measuring this is something called RAA, the nuclear modification factor, which is, I've just sort of written the equation here. What you do is you count the number of particles at a given momentum that you measure in a lead nucleus, and you compare that to the number of particles at that same momentum in a proton-proton collision. Of course, you expect there to be more in the lead nucleus because you've done more collisions, there are more nucleon collisions. So you have to scale this somehow by the number of proton-proton collisions that you would need in order to argue that you would have the same as a nucleus-nucleus collision. This TAA, this nuclear overlap function, this is something that you can calculate in principle, but without a sophisticated nuclear NPDF, you actually get the wrong answer. But it's not too wrong, because here's a plot of like early data. When I was a PhD student, my supervisor showed me this plot and said he wanted it on a t-shirt because it shows this physics very carefully. And I've never used a different plot actually, because it just talks about the physics very clearly. So you see here the suppression of pi zeros and etas. So the red dots and the yellow triangles, that they are significantly less than 1. But the purple squares are photons, and they are really sort of within these uncertainties, that's really 1, which means that I've done whatever I've done, I've sort of maybe done this scaling correctly, because the photons are not affected by the medium. So you should get 1, you should get an RAA of 1 for photons. But then here's a significant suppression, and you can do an analytical calculation as well, and this yellow line, and that sort of gets the physics right. Okay. So this is how we understand, this is sort of the lore of jets. This is how we think we understand what's happening with jets. What we're starting to realize is that like a lot of the story doesn't really bear up to careful scrutiny. So one of the things you try to do is, okay, let's try to see if we can understand precisely what's happening in the jet. So what I've got here is a diagram. Actually saw that there's quite a bit of light in your, I don't know if you can see this diagram clearly. I hope so. Maybe not, maybe you can't see the plasma that I've drawn on the back, but okay. Here's a produced particle. It will sort of travel into, it has some time before it splits. And then if your quark antiquark, now out come this quark antiquark pair. And you have some sort of interaction with the medium, and what's all of these, this very high momentum, far off shell quarks are radiating gluons. There's a lot of things, there are a lot of things happening here. They're splitting themselves. And then eventually I sort of think about maybe, okay, I start to hadronize some of these quark antiquark sort of things that are happening here. I hadronize them in some system. This is clearly here Lund string model. So you've got some splitting, oops, hadronization here. Then there's some interaction between my hadrons, and off they go into the detector. Good. So I can do this analytically. This Liliana, I saw that Liliana gave a talk earlier in the year in CTMP. So it's, but that was in February already, and I don't remember very much about what happened in my life in February. But those were two excellent talks, and she talks a lot about these sort of analytical calculations. And actually, I took this diagram straight from her. So if you are curious about how this is done analytically, you can really have a look at her talk. Of course, if you don't want to do this analytically because it looks like a mess, and in fact, when you do this analytically, you have to make a lot of simplifications. You have to really sort of think of very specific limits, and you have to do things in a particular way. You could, of course, try to do this in a Monte Carlo generator, which is what we are going to talk about a little bit now. So if you do this in a Monte Carlo, you still have to make a statement about what you think is happening in nature. So let's see what happens in Monte Carlo jets. So there are two ways to do jets in Monte Carlo. The first one is that, okay, you start off with your shower, so say some sort of vacuum shower, but in order to model this vacuum shower, what you do is you do the whole vacuum shower, but then you modify the developed shower. So you don't change. So the vacuum shower is known as, you start off with a parton shower, and this is known very well from PP. And then all you do is you say, okay, well, I'm going to sort of smear this in some way, and I add some modification here. One of the problems here, if you do it this way, is that you are really modifying the low momentum parts. By this time, by the time you reach the sort of later stage of the parton shower, you're modifying the low momentum things, which means that you are potentially playing around with non-perturbative modifications, which is a little bit dangerous. You might not really know how to do that. But okay, that's fine. I can include these medium-induced effects from transport coefficients, and this is done in, there are sort of several different Monte Carlos that do this. Okay, the other way to do this is, of course, instead of modifying the shower at the end, you go into your vacuum shower. So I start off with my vacuum shower, but every time I have a splitting, instead of using the vacuum splitting functions, which are known, I modify the splitting function. So I look at every splitting and I pretend, okay, here's a modification to the splitting due to the medium, and then I will evolve a little bit further in vacuum, and then I sort of have another splitting which is modified by the medium, and so on. And so the Monte Carlo codes that I work with generally follow this. The problem that you have here is that you have to rely on a chosen shower. So you can't, these parton showers really are making a statement, a classical statement about nature, right? This is essentially a classical diagram. There are no loops here. And I haven't really taken the quantum mechanics into account. And so I'm sort of saying, oh, okay, I have these splittings, and I can put a little bit of quantum mechanics in there, but really I have to order my splittings in a particular way. And there are different ways to order these splittings. But if you choose this option on the right-hand side, then you have to choose a shower and modify the splittings in that shower. But if you take it on the left-hand side, you could just evolve any shower you want, and you can modify that. You take any shower easily, evolve it, and then at the end, you modify you add a medium modification to the end. And so there are sort of pros and cons to each of these options. Okay, maybe let me just see what was. Oh, okay. Let me pause here again just to see if there were any questions or if I've skipped over this a bit fast.
So just a question about, so you're talking on the, for us, the right-hand side of the, the modifying of splittings.
Mm-hmm.
You said it's, you have to pick a particular shower to do this. I don't think I quite fully understand. Is there no general prescription to say, I have one split, I can now replace it? Or is this now far more complicated than that?
Yeah, it's more that I'm talking about choosing a particular type of vacuum shower. So you, there are different, so for instance, one of the choices you could make is you could say, okay, I'm going to have my, I'm going to order my shower in the, in virtuality. So I say, okay, if I highly virtual particle will shower in one way, and then in a different way when it's at a lower virtuality and lower virtuality and lower virtuality. But I can also order this shower in a different way. Now, of course, as I'm sitting here, I'm like completely blanking on what else you could do. But okay, but there are different order variables. They're sort of time variables and there are mass variables. They're not exactly those ones. They are different technical names. But anyway, so you can choose the shower. You can create a different shower. You can create this parton shower, which is a Monte Carlo thing, right? I've written a piece of code that does this, and I have to make a choice about what's happening, about how these splittings are applied. Now, what I'm trying to argue here is that you can't. Of course, you could choose a shower. You choose a specific shower, and you modify its splittings. Fine. And then you could choose a different shower and you modify its splittings. But every time you do that, the modification is something different because you're modifying a different rule for how you split. So the medium effect on the splitting is different. On the other side, if you're not sort of bounded in this way, this modification is done at the end of the shower, which in principle, if you've written a good parton shower, all of them should produce the same end result, right? They should produce something that you can compare to data. So at the end, these things are all giving the same results, and I can modify them in the same way. But if I want to do it here, I have to be careful about precisely how I'm doing these different modifications at each splitting.
Okay.
But there's no general prescription for what is a parton shower and how you should do a parton shower. Okay, good. So, okay, good. So one of the things you could do, so there's a piece of code which is also freely available. This is also open source code called Jetscape, which puts everything together. So, and in fact, this you will recognize if you were at Björn's talks, you will recognize this this animation at the top here. I've taken this slide from Chun Shen, or parts of the slide from Chun Shen, who works closely with Björn on these things. So in Jetscape, what you have is you have this sort of full evolution. You have this initial state. You have some pre-equilibrium dynamics which is sort of done in a particular way. Then you have the hydrodynamics and you have hadronic transport at the end. And then what Jetscape is able to do is to evolve a jet on top of this in a way that is careful to be able to allow you to have the jet actually modify your hydrodynamics as well. So you evolve it at every step. That means, so you resource the hydro, right? But that means that the code is very slow. You're not going to run it on your laptop. You can run it on your laptop, it'll take you ages to run like a few events. Okay, you could do this. Actually, so Jetscape is it's a very large collaboration, and they've done a lot of physics, and they actually run a free online summer school every year. I looked for the 2024 one and I didn't see it, so I don't know. But anyways, I put the link here for the 2023 one. All of their videos are online. They have like a bunch of, they walk you through how to run the code and so on. And so it's also a very nice exercise as a student to sort of see if you can download this and run some events. And it also allows you to run music easily because it comes prepackaged with music and so on. Okay. What's interesting about the way that they evolve the jet is that they have included some physics here, which is not often included in parton showers. So they have a two-stage, or like they call it multi-stage evolution. They really have, at a very large virtuality, they have one way of evolving this jet, and then they have some sort of cutoff. So it's a parameter in their model. They have a cutoff, and then after that, they have a different. They sort of do this shower or this modification in a different way, which is very sort of interesting because it turns out that it's quite important. It's quite important that your when your parton has a very high virtuality, it's really actually almost evolving as though it's in vacuum. It can't see the medium at all. It's really doing some sort of vacuum evolution. And then later on, it has this modification due to the medium. This LBT way of evolving the jet, this is one of these sort of the first or the left-hand side option. It evolves the jet and then modifies the shower later on. Okay. And then I just showing a quick result here for this is the jet RAA, and they compare to Atlas and CMS data. And okay, fine. So they have many parameters, and they can do a tune, but they've also done they do this tune not just by hand. It's really a full Bayesian study. So they've done a sort of, they can really fit a huge variety of high PT observables, and they're able to do this quite sort of nicely. So okay, so there's Jetscape, which is very nice. It has everything in it, and in principle, it's supposed to be quite modular. So it's supposed to be written in a way that you can, if you have your own energy loss model, so suppose you wanted to put in a different energy loss model in the middle here, you can actually take theirs out and put yours in. So it's supposed to be written in that way. But it turns out that somehow the community hasn't used it in this way, which is somehow a pity. But I think because it's in principle, you have a framework here that allows people to use different state-of-the-art physics without being experts in all of them. So it's nice to play with, but it turns out that really it's the Jetscape collaboration that is doing this, and not so many other people. Okay, I want to talk about Joule because Joule is, because next week we'll talk a lot about the results from Joule. So Joule is Monte Carlo jet evolution. So it's sort of this is an acronym. It stands for jet evolution with energy loss. So what Joule does, Joule is really a parton shower. It's a vacuum parton shower, but then with some media modifications to each splitting. So now we're on the right-hand side. Now we're talking about this option. So you have a vacuum shower with the medium modification, and it has a formation time veto. So it sort of says, okay, if the formation of this gluon is too slow, or it takes a long time, but you scatter again, then the scattering with the smallest formation time will create the gluon and so on. So it's the physics of this is very clear and easy to follow. So the way that Joule works is you start off with some production. So you use Pythia. So Pythia is a sort of a general purpose event generator used in PP. So Joule starts off with Pythia. It has a look at the parton distribution function, and recent developments in Joule allow you to really use a nuclear parton distribution function. So you pull a jet out of this. You then have a vacuum radiation according to declap evolution. So fine, you have some vacuum radiation, but then you can include a medium. So you can do this in vacuum, but you can also include a medium. And what Joule ships with is a simple medium. So they've just sort of said, okay, I'm just going to take, first of all, nothing happens in this pre-equilibrium phase. There's no temperature, nothing. Oh, actually, they have a linear temperature rise. So it's sort of from 0 up to some high temperature. Fine. And then I just evolve my jet. So I start off with some quark that's coming. I then have an interaction with the medium, and I ask the medium what the temperature is, and then I do a 2-to-2 scattering, and I can keep going with that. This medium that Joule has, though, is quite simple. It's really just a Bjorken. It has some energy deposition that comes from overlapping Wits axons, and then with some ideal gas law that gives you a temperature and so on. And then there's a very simple Bjorken expansion, which means that your your medium is expanding longitudinally. So in the transverse direction, it's not expanding, it's just cooling down. So you have this cooling down over time, and in some way, this is a reasonable approximation in a central lead-lead collision that you could do well. Okay, so then once Joule has done this, so it produces a parton, it can do a vacuum shower, but it can also put this vacuum shower on top of a medium. And then once it reaches some TC, it will give this jet back to Pythia, and Pythia will create an event, sort of a list of particles, really. It creates a list of particles. And now you can play with this list of particles. What Joule allows you to do now is that you can actually turn recoils on in a way. So that allows you to look at what happens. So this jet is moving through the medium. It exchanges energy momentum with the medium, but that means that it could be like kicking the medium, right? So you can have some back reaction from the medium. So Joule allows you to track. I can now have this momentum, this medium particle move off and itself become a Joule particle that sort of showers and can interact with the medium and so on. In practice, this is a bit of a problem. You have to you run out of memory very quickly. So if you don't have huge amounts of RAM, your the event record actually fills up quickly. And in fact, that's actually limited. Even if you have a lot of RAM, at some point more RAM doesn't help you. The Pythia event record fills up. So okay, you can't really do this very much, but if you have a lot of computing power, you can keep going a little bit. Okay. Oh, I'm sorry. I just spoke about this slide. I could have explained this better. Right. Okay, good. So here is just a diagram which shows how Joule really actually do this. You can have your quark and anti-quark going. They scatter here. You have initial radiation as well. They scatter here, and then they sort of go off, and they can radiate, and the scatterings themselves can radiate as well, and so on. So okay. It's just that the Joule can keep track of all of this and give you a very nice event at the end of the day. Okay, I wanted to very briefly talk about co-LBT, just because I've mentioned this back reaction. So there's, once the jet is scattering off the medium, it actually imparts momentum to the medium. Of course, that's what we're saying. We're saying the jet is losing energy. It's not really losing energy. It's imparting momentum to the medium. But that means maybe you can measure that. And so what they have done in this simulation is they use this same LBT energy loss, which is in Jetscape. But so here's a picture of, this is the gamma jet. So there's a photon coming out and then the jet coming down in this direction. And what you see is that this creates some kind of Mach cone. So you create so in this picture down here, you see that there's so you have this cone that's happening exactly going through air on a lake or something. But okay, at the end of the day, the point is we are now, the Monte Carlo generators are sophisticated enough to actually be able to model this back reaction in the hydrodynamics. In order to do that, you need extraordinary computing power. You really have to, you are running your hydrodynamic simulation, and then at every time step of your jet, you are resourcing the hydrodynamics and running it again and keeping and going on in that way. But they have come up with some nice observables and ways that, because it's a very, of course, a lot. Is there a question?
You're coming through somewhat choppily. Okay. Ironically, you have people from all over the world, and coming in from Johannesburg apparently is too much for the internet today.
I'm so sorry. Not quite sure how to solve this problem. I can try to move to a different part of the house. Okay, well, okay, so I'm almost done in any case. I wasn't. Sorry, I'm sorry. I apologize for all the break. Good. Okay, so the main point was just these Monte Carlo, these generators have become very sophisticated, but you do need a lot of computing power. Okay, then there's this question: what if there's no QGP? What if all of this physics that we're seeing, all of this, everything we've seen this all of this like flow and the modification of jets. What if that's just some sort of high dense fluid dynamics? People have tried to do this. They've called it's Angantyr. So it's built on Pythia. Angantyr is some Norse. I've forgotten exactly. It's some Norse god. But what the folks at Lund have done is they've taken Pythia and they've increased the number of particles in a given collision, and they've sort of pushed these things a little bit in physics out. And what they I'm not sure, my apologies. What they have found is that, okay, if you really, you can get quite far. They can't really get they can't really get the jet quenching in a central lead-lead collision, but in smaller collisions they can reproduce a lot of the physics. And in fact, they can even reproduce a lot of the V2. So here's V2 on the right hand side in this plot. So now for very sort of central lead-lead collisions, they're really able to get some of this physics right. Of course, it looks like they don't always get it right, but just by adding in some additional rescattering, you just add in scattering, you get a lot of this V2 physics. So now you can ask the question, okay, how would you know? How do you know whether there's a QGP or not? Which maybe we should have asked, since I wanted to flow into the small systems. Let's just sort of look at what it is that, how do you distinguish between one and the other? And the argument is the following: you have to have there's no smoking gun for the quark-gluon plasma. You have to have all of these very different signatures of the quark-gluon plasma, all described within one unified picture. So you have to have this low PT physics, or the flow and so on. Now we're finding that low PT physics can be reproduced in a lot of different ways. Angantyr can get it. You can have hydrodynamics can get it. And okay, then you have to have this high particle as it moves through the medium, or not. Is there a way to describe the modification of jets in a lead-lead collision, some kind of medium? And of course, then the crucial point is that you need a control experiment. You need to have an experiment where you know that there's no QGP at all. And then can you still hear me?
Sorry. You're coming through choppy. What might help is if you
can you still hear me? Oh, you have a question?
Yeah.
Turn off my video, you say?
Yeah.
Maybe I'll stop the video.
Yep. Maybe that helps.
Okay, maybe that helps. I can hear you just fine. So
You're coming through well now.
Okay, I'm almost done. Okay, let me. Oh, really? Okay, great. Good. I mean, I'm basically done. So let's. So the argument is just, if you have this low PT and the high PT, you really need a control experiment. And what happened was that people tried to do these control experiments. So I was looking initially at like producing this quark-gluon plasma in the most obvious place possible, very central, high energy lead-lead collision. But suppose I want to measure a few things. Maybe I have like a proton-proton collision, which is my control experiment. But there's this big jump between the proton-proton and the lead-lead. Can I do an intermediate experiment to measure some of the properties of the lead nucleus without producing the quark-gluon plasma? So you do these proton lead or deuteron gold collisions, and you find very, very quickly that this beautiful picture that we have of there's flow and there's jet quenching and there's I've chosen these two signatures. There are many others, and they are all there in the lead-lead collisions, and they shouldn't be in the small collisions. And you find that actually some of them are in the small collisions and some of them are not. And I know Björn spoke a little bit about this last week, but what I want to talk about next week is what do we do about these jets in small systems? Is it possible to really model, to know exactly what our theoretical understanding is of jets in small systems? Do we understand why that signature of the QGP is not there? Okay, so maybe just quickly in summary, I spoke about that these like heavy ion collisions contain a lot of physics. There are all these different stages, and it makes the modeling quite difficult, especially if you're trying to do it all analytically. You have a lot of strength and power in Monte Carlo generation, because you are able to add in all of these different pieces of physics. But it's not always clear how to do this. And there are lots of different ways of doing this. Some of it is freely available, some of it is not. So you can play around with that. And then next week, what I'm going to talk about is I'm going to take this physics that we've now talked about, the background hydrodynamics, the jets, how you do this in Monte Carlo, and then we're going to see if we can apply this to small systems and what you find. And so here's just a teaser plot of running Joule on music. So this is on this hydrodynamics that we had before, but doing it in different system sizes. So here I've got in red, I've got lead. This is the jet mass and lead. And try to see if we can find signatures of the quark-gluon plasma in these sort of smaller systems from. I apologize for the broken connection. Are you all still there? Oh no.
Yeah, I think the last bit came through slightly out of sync way, but I think we got the gist. I think
Sorry.
we managed to get even more people in the middle of the talk. So it's such a good talk. The word got out, and the room literally filled up. Okay, good. So any questions? So thank you, Isobel, for answering questions during the talk, which was very nice. Are there questions from the floor now that the talk is concluded? Oh my gosh. Okay, Daniel, go ahead.
This might be an unfair question. You talked about how the jet modified the medium, that you could do this. You could do some simulations of this. That seems really hard to measure experimentally, just because I imagine the region where it's modified is very close to the jet. And it seems like you'd run into issues of what is the jet and what is the medium. Do you have any idea how they would do that?
Yeah, no, you're absolutely right that it's an extremely difficult, it's a very, very difficult measurement experimentally. You're right also that, yes, precisely one of the problems that you have is you're looking in the direction of the jet, and what we traditionally do is you try to subtract out the medium in order to look at the way that the jet was modified. If you now want to include the medium, you have to know what it is that you want to compare it to. An interesting option is to so this whole time I've been talking about looking at the jet in this transverse plane. So the plane transverse to the beam at mid-rapidity. What you can do is look at correlations that are in the longitudinal direction. So you now sort of look at what is happening to the medium in this as it's expanding longitudinally, so that you can look longitudinally away from the jet, but you're still affected by the jet there. And this is one of the predictions that came out of, I haven't shown it here, but that came out of this CoLBT calculation, is that you would see a significant modulation in eta. So I didn't actually draw a diagram of these variables, but okay. So if phi is the angle perpendicular to the beam, then eta is this angle longitudinal to the beam, and you would see a modulation longitudinal to the beam. But of course, then what you have to have is very big longitudinal acceptance in your experiment, which coincidentally Alice 3 will have. So Alice 3 is hoping to, well, okay, it depends who you talk to. If you ask some people, they will say, we want 10 units of rapidity. It's not likely that they will get 10 units of rapidity, but they will certainly have 5. So 5, sorry, I mean, well, okay, yeah. So they will certainly go up to sort of minus 4 to 4. So that's sort of 8. So that's, so then you might be able to measure this for sure, yeah.
Okay, super. Ben, please go ahead.
So maybe just a bit of a basic question, but I wasn't exactly sure when you had the splitting of the parton trials, why exactly do you need to modify those?
Well, what you're trying to do is include the effect of the medium. So okay. So what I'm working on I'm sort of working on a sort of operational definition of a jet as something that, or as the medium modification of the jet, as I'm really imagining having a vacuum jet and whatever it is I understand this jet to be, which also next week we'll talk a little bit about precisely what is a jet. But if I am operationally, I'm thinking of taking a vacuum jet, which I understand from proton, and I want to ask how this is modified by the medium. And if I want to do this in a Monte Carlo, if I want to do it step by step, I have to think about, instead of trying to create some different system in which you have a jet which is living inside a medium, I'm really thinking about this vacuum jet which is modified by the presence of the medium. And so I want to modify things that I already know, right? I want to start with something I know. And what I do know is the vacuum shower. Well, I can control that more easily experimentally. Yeah. So in that sense, I'm thinking about how do I modify this vacuum shower to imitate to imitate the presence of a medium.
Thank you. Super. We have 2 comments in the chat. Jared says, "Thank you for the talk, Isobel!" Exclamation point. And then a question from Lorato asking, while running the co-LBT simulation, is it possible to get the hydrodynamic quantities that might describe the momentum distribution, the flow coefficients?
Yes, absolutely. Yeah. Oh, well, I say yes, absolutely. I've never done this myself. I'm going to say I don't know. My immediate reaction was yes, absolutely, should be able to, but I'm going to take that back and say I don't know that answer. But if you would like to, you can just send me an email. I will check in with Shinyan and ask him, and I can email you back the answer I just need your email address.
What's your email address, Isobel?
It's isobel.kolbé@wits.ac.za. I have a website. If you Google me, the information is there. I have my own website, so then you can find the information there.
Awesome. Very good. Very good. Cole, please go ahead.
Hi. Yeah, so related to the splittings, it seems like it seems like you talk about a few sort of theoretical issues when you go more differential when you're thinking about the vacuum showers. So from what I understand, the modification of the splittings is sort of not as theoretically easy or maybe sound as doing a calculation where everything's more inclusive. And then there's also this ordering problem that you mentioned. So maybe you could just talk about what advantages you gain by looking at things more differentially. Is it accessing you seeing more substructure? I guess there's more observables that you can access. Like, what advantages are there over just a normal leading hadron RAA?
Yes. So this is a favorite. This is a sort of pet peeve of mine. Well, I say pet peeve, but a favorite. I'm so glad. This is a great question. Thank you. I get to give my opinion freely. So I have the problem with RAA is that it's very useful in lead-lead collisions where the signal is large, where you really have where you're not too sort of worried about small effects and so on. What happens in small systems, which again we'll talk about next week, it turns out that RAA relies too much on a whole bunch of different things to go exactly right for you to get a result. So for instance, you have to know exactly how to compare things. So this TAA, this scaling factor over here, this is sort of clear and obvious. Oh my goodness, I have a backup slide which I decided not to put in here which literally is called why RAA is the worst. Okay, good. So the one thing is that the scaling factor here does not work well. It's very difficult to calculate in small systems. So suddenly your interpretation of RAA becomes very difficult. And so it's not even just a question of how much physics can you access if you look at other observables. It's really a question of do you gain any physics knowledge at all from using RAA in small systems, because you have no idea what it means. You don't know how to interpret this. And okay, it's a bit of a
Isabel, you're breaking up. You're breaking up at exactly the point where
answer because
got all of
experimentalists have done a lot of this and so on and so forth. But this paper that you and Will wrote, where you confused up a bit.
Fast forward.
Yeah. So you got our.
I'm sorry.
Yeah, you got our undivided attention by saying RA is the worst, and then you started talking about why it's the worst, but then all of the good bits got eaten by the internet.
Oh no.
Can you do the whole thing again?
Okay, good. So what happens is that in order to have a clean interpretation of RAA, you have to know what the scaling factor is, this 1 over TAA. So here I've written TAA because we've just assumed in AA collisions that the scaling factor is just this average, the average overlap function. You just want to know how many nucleons have collided, right? But it turns out that relationship is very clear in lead, and it's easy to calculate. It's easy to extract from Monte Carlo. But in small systems, this relationship is not clear at all. You are dominated by the nuclear parton distribution function. You're dominated by these by the early phases, and you have no way to calculate how many
You have no way to calculate, I'm guessing, the TAA, but now again
have collided. Remember that in experiment what you measure is collided. So in small systems, all of this tweak and make sure that I have better connection. How about
that? Very good. And we'll look forward to having actually even a slide. Maybe because this just is kind of getting to hopeless internet. I guess everybody in Johannesburg is on Netflix or Pirate Bay downloading their movies tonight. I think we'll call it a day for this time. But really, this is fantastic. Thank you so much. And maybe you can call in from Wits itself on next week.
Generally, that's worse, but I will try. Sure.
Yeah.
Right.
Super.
Fantastic.
Thank you so much.
Thank you for having me. Thanks. Cheers.